Today we're going to look at derivatives of special functions. They're called transcendentals, and these would be our trig functions, e to the x, the natural log of x, functions that aren't your normal standard polynomial functions. So we're going to start off and we're going to do this graphically, a little more intuitively than deriving something. Here's my basic graph of the sine curve, and my x-axis is in terms of radians, but it's not in terms of pi, so we'll just kind of do a little estimate here. So I'm going to look at the slope of the tangent line at different points of that curve. If I look at 0, the slope of the tangent line is a 45-degree angle, so that slope is going to be 1 over 1, and we have a slope of 1. At pi over 2, which is a maximum point for sine, if I think about what the slope of that line is, it's horizontal, so it has a slope of 0. And then at pi, we have a negative 45-degree angle, so that's negative 1. The slope of the tangent at 3 pi over 2 is 0 again, and then the process repeats itself. We're back up to positive 1. So if I were to sketch the function of the slope of the tangent line, I would put some points in. At 0, I'm at 1. At pi over 2, I'm at 0. At pi, I'm at negative 1. At 3 pi over 2, I'm at 0 again, and then at 2 pi, I'm back up at 1. And if you sketch this, and if you were to take more points, it looks like a very common curve. In fact, it ends up being the cosine curve. So the first derivative of sine is going to be cosine. So now we're going to do the same thing starting with the cosine curve, and we're going to look at the same locations and look at the slope of the tangent line. So if I start when x is 0, I have a horizontal line, my slope is 0. When x is pi over 2, I have a slope of negative 1. And at pi, I'm at 0 again. At 3 pi over 2, I'm at positive 1. And at 2 pi, my slope is 0 once again. So if I were to graph this, I start at 0, 0. At pi over 2, I'm at negative 1. At 2 pi, I'm at 0. At 3 pi over 2, I'm at positive 1. And at 2 pi, I'm at 0 again. So sketching this curve, it's not exactly the sine curve. In fact, it's the sine curve reflected over the x-axis. So this is actually a negative sine curve. So that's a way we can graphically derive first derivatives for the sine and cosine by looking at what the slope of the tangent line is doing at various points. So to summarize the first two transcendentals we're looking at today, if f of x is equal to sine of x, then the first derivative of sine is cosine. The first derivative of cosine is negative sine, so don't forget it's not a regular sine, it's negative sine of x. So those are our first two transcendental functions. We're now going to look at e to the x and the natural log of x. So the function f of x is equal to e to the x. It's got a special property because the first derivative of e to the x is actually e to the x. So it's the only function whose derivative is the same as the function itself. In one way, that makes it very simple, but what you'll see when you start doing problems, it can be a tiny bit confusing to remember, well, is this the derivative or is this the original function? So we've got to be careful. But the first derivative of e to the x is actually e to the x. And then finally we have our transcendental f of x is equal to the natural log. The first derivative of natural log is 1 over x. If you remember, we can't, there's no function, thinking of the power rule, there's no function using the power rule where I take the first derivative and get x to the negative first. Because to do that, I would have to start with x to the 0, and the power rule doesn't really work. But it does turn out that the first derivative of the natural log is 1 over x. So all of these together, if I have y is equal to the sine of x, then dy dx is the cosine. If y is equal to the cosine, dy dx is negative sine of x. The derivative, if y is equal to e to the x, then dy dx is still e to the x. And then finally, if y is equal to the natural log of x, then dy dx, the first derivative is 1 over x. Those are our 4 transcendentals we're going to work with today. So now we're going to work through some examples using these transcendental functions along with the rules we have already learned. So my first example, y is equal to x squared times the sine of x. For this one, we can use the product rule because it is a product, and the only difference is I'm going to have to use one of my transcendental rules to finish it. So if I'm using the product rule, I know u of x is x squared, v of x is going to be sine of x. Taking their first derivatives, I have u prime is going to be 2x, and now I know that v prime, the derivative of sine, is cosine. So my first derivative, dy dx, that's Leibniz notation, it's going to be x squared times the cosine of x plus 2x times the sine of x. And there's really no other simplifying that you can do. You could factor out an x, but it's not necessary. There's your final answer for that one. For my second example, I have x cubed minus 2x plus 1 in parentheses, and I have e to the x. I'm going to use the product rule again. You could distribute and then just use the power rule, but if I use the product rule, u of x is x cubed minus 2x plus 1. V of x is e to the x. And so u prime, I'm going to use the power rule here, 3x squared minus 2. V prime, the derivative of e to the x, is just e to the x. So f prime of x is going to be x cubed minus 2x plus 1, there's u of x, times the derivative, e to the x, plus 3x squared minus 2 times e to the x again. You could distribute and combine like terms. If you did that, or I could actually bring my e to the x out in front, e to the x, and then I have a bunch of terms, x cubed minus 2x plus 1 plus 3x squared minus 2. So here's one way to represent the derivative, e to the x times x cubed plus 3x squared minus 2x minus 1. And that's using the product rule. And we have one more example using the product rule because I have a product of 1 over x times the natural log of x. So one more time, u of x is 1 over x. V of x is the natural log of x. U prime, if I think about what u prime is, if I rewrote this guy to find it, let me start off by just calling it u of x. If I rewrite u of x as exponents, that's x to the negative first. So using the power rule, u prime of x, I'm going to bring the exponent down in front. That's negative 1 times x to the negative second power. And then v prime is going to be 1 over x. So when I put everything together, dy dx, u of x is 1 over x. v prime is 1 over x plus u prime. If I wrote that in with positive exponents, is going to be negative 1 over x squared times v, which is the natural log of x. So this is 1 over x squared minus 1 over x squared times the natural log of x. That's one way to represent this. You can combine terms. You could factor out a 1 over x squared if you wanted to keep going. Finally, we're going to look at the tangent of x and try to find the first derivative of that. To do that, I'm going to rewrite this. F of x, instead of tangent, I'm going to rewrite it as sine over cosine. When I do that, I'm going to use the quotient rule to find the derivative. So, f prime. Using the quotient rule, it's going to be low, which is cosine of x, d high, the derivative of sine, is cosine, minus high, d low, the derivative of cosine, is negative sine, all over low squared, cosine squared of x. That means I have cosine squared of x. My two negatives multiply and create a positive times sine squared of x, all over cosine squared of x. So this is the Pythagorean identity, cosine squared plus sine squared. That's equal to 1. So the derivative of tangent ends up being 1 over cosine squared, which is the same as secant squared of x. So you can use your derivative rules to find derivatives of all sorts of different functions, and we will practice more of that in class.